Okay, thank you very much. So what I wanted to do in this talk is first review the old but still, I think, truly remarkable story of relations between black holes and thermodynamics. Then I briefly mention, well, one newer result, and then I just want to leave things, though, with the issue of how do we understand black hole thermodynamics and argue that we're really not only going to need a deeper understanding of gravity and quantum theory, but also of statistical mechanics. So that's where I'm going. But what I'll be doing in the first half of this talk, certainly, is reviewing the main story of the relationship between black holes and thermodynamics. And to get you in the mood and get things started for this, I want to bring out an analogy, not a spectacularly wonderful, I mean, it is a wonderful analogy, but not one that's going to convince you that there's a lot to the subject right off the bat, between stationary black holes and bodies in thermal equilibrium and how we approach these and how we approach these. So I want you to consider, on the one hand, just some ordinary thermodynamic system, or ordinary mechanical system, I really should say. A gas, let's say, with a large number of particles, then you dump the gas in some basically random way in a box. And if its state when you dump it in depends on the details of how you filled it up and all sorts of complexities of microscopic dynamics. But if you wait long enough and look at macroscopic sort of observables, you'll see that the gas will settle down to some state that usually is referred to as thermal equilibrium. Of course, it doesn't really settle down to some one definite state. It's really moving around as much as always in phase space. But as far as the macroscopic observables you're looking at is concerned, they're not changing. So it appears to be in thermal equilibrium. And these thermal equilibrium states are characterized by some rather small number of state parameters, especially given that we might have 10 to the 25th particles in this box. Just having like 3 state parameters is a big reduction in the description. The total energy will always be one of the state parameters, and it's conserved in this case of the box. Number of particles you put in and total volume are really the only other state parameters. Well, similarly, if you form a black hole by gravitational collapse, well, what that black hole looks like as the collapse is taking place, or very, very shortly after it has taken place, is going to depend a lot on the details of what the star or whatever it was made of, how it collapsed, its shape, and things like that. But one of the things that was learned in the late 60s, early 70s is that, well, it's not been proven, but it's certainly believed that it will settle down very quickly, in fact, to a stationary final state. I'll actually come back to that later. And this stationary final state, as was proven in the 60s and 70s, primarily late 60s and early 70s, is also characterized by just a small number of state parameters, total mass certainly being one of them, angular momentum, and if you allow electromagnetic fields, the electric charge Q would be another one. If you allow more matter fields of appropriate types, you could have other state parameters. This isn't some complete and final list. The point is there's just some small number of state parameters, just as this is not some complete and final list of all state parameters you might have in other systems. Okay, but what's really starts getting remarkable is that there are laws that hold in general relativity for black holes that are completely analogous to ordinary laws of thermodynamics. So in ordinary thermodynamics, if you have something that's sort of locally in equilibrium, you can define a notion of temperature. And in thermodynamics, a statement is that if you have a body that is truly in thermal equilibrium, not just locally, its temperature will have to be uniform over the body. Well, I'm only bringing this out. That's not such a remarkable and possibly not even such a deep statement in ordinary thermodynamics, but it's remarkable that there's a close analog of that for black holes. If you have a stationary black hole, you can define a notion, so stationary being analogous to equilibrium, you can define a quantity known as the surface gravity of the black hole, which you would not in general be able to define if it wasn't stationary. And the stationarity is used because ordinary surface gravities are, in freshman physics, are accelerations of bodies that you drop near the surface of the Earth. In general relativity, those accelerations are zero, actually, but if you can ask what acceleration, what force do I need to use to hold a body in equilibrium, keep it stationary. If you approach a black hole, the force you need as you approach the horizon to keep a body stationary, or the acceleration you need to give, the local acceleration, diverges to infinity. But if you multiply that by the redshift factor, then you get something that always approaches a finite limit, and it's a theorem, a non-trivial theorem in general relativity, that even if you have a rotating, non-spherically symmetric black hole, this surface gravity has to be constant over the entire horizon. Okay, well, that's not so incredibly amazing either yet, but it starts getting a bit amazing when one sees the analogy between the first law of thermodynamics and an analogous law for black holes. So the way I would formulate the first law of thermodynamics is, first of all, that there's a quantity one can introduce for this thermodynamic system known as its entropy. And if you make a little change from one equilibrium state to another, the change in the entropy, well, it'll have to be related to the changes in state parameters, but it's related in this way that I've written here. Similarly, for a black hole, we can introduce nothing can stop us from defining this quantity A to be the area, the ordinary surface area of the event horizon of the black hole at whatever instant whatever cross-section, whatever time we want to be calculating it. And if we do something to the black hole, like throw some matter in, well, it'll change its area, and it will also change its state parameters. Those changes are related by a formula of exactly that sort, where, well, energy and mass are playing the same role, surface gravity and temperature are playing the same role. These terms may look completely different, but these are work terms of exactly the same nature that you have in thermodynamics. If I considered the thermodynamics of a rotating body or a charged body, I would have exactly these types of terms appearing in the ordinary first law of thermodynamics as well. But what's truly remarkable is the analogy between the second law of thermodynamics and, well, the so-called area theorem, the classical area theorem for black holes. Right, second law of thermodynamics says that total entropy of the universe never decreases, or total entropy of any isolated system never decreases, I mean, with appropriate caveats, as came up in Carlo Rovelli's talk and so on. On the other hand, it's a theorem in classical general relativity that if you have locally positive energy falling into the black hole, and of course assuming that the black hole doesn't get destroyed, that's another assumption, the area of the event horizon can never decrease. Now, there aren't very many monotonic in time laws of this sort, and it's really rather remarkable that one has in classical black hole physics this relationship. So if we look at the analogous quantities, I've chosen a particular numerical factor here with the foresight in this talk. Right, one has an 8 pi coefficient here, so that can be distributed at this point any way I like between the kappa and the A. But if I distribute it this way, these are the analogous quantities in all of the laws. And a hint, even in classical physics, that this might be a little more than a mathematical analogy is the fact that in relativity theory, mass is energy. So these analogous quantities here that are playing the same role in the laws are actually physically the same quantity. So that's rather remarkable. But if you go down further on the list, that's, I claim, the end of the analogy in classical, the end of the physical analogy. The mathematical analogy is perfect because it's clear that the temperature of a black hole is indeed in thermal equilibrium as a thermal system classically, but it's at absolute zero temperature. Well, except that when we take quantum effects into account, the story gets, far more interesting. Black holes, when quantum field theory is taken into account, are still perfect black bodies, but at a finite non-zero temperature. And even more interestingly, that temperature is given by this surface gravity quantity that appears as the analogous quantity in the laws of black hole mechanics. And that's why I chose this 2 pi factor in that analogy. So the black holes, of course, don't actually emit anything. So they do this in a rather remarkable way. There's particle creation near the black hole, of which some of the stuff comes from near the black hole, but would look to a distant observer as though it were coming from where the black hole is. It really looks like it's coming from a white hole that you might assign to this, by mathematical continuation, to this black hole. So this, of course, temperature is not very large for macroscopic black holes. It's not an important effect in astrophysics unless we have primordial black holes of very tiny mass. But as a matter of principle, there's an extremely important issue that black holes can, in fact, instead of being ultra-stable objects in classical physics, they, in fact, can evaporate if they're in isolation or surrounded by lower temperature, or zero temperature preferably. They'll evaporate at the Stefan-Boltzmann law kind of rate, which gives an estimate for the finite lifetime of a black hole, because as they get smaller and smaller, they get hotter and hotter, and that dominates the diminishing of the radiation due to their area getting smaller. Okay, so if we get back to this analogy, now we've got actually a check mark on this second line, which is, which would not have occurred in classical physics, but with the h bars in, this really is the Hawking temperature of a black hole. What about, now we've got the coefficient fixed, what about area and entropy? Is the area of a black hole really its physical entropy, or is it merely some quantity that's mathematically playing a similar role? Well, the way to test that and see what's going on is to consider the interaction of black holes with other systems and seeing what role in that context its entropy, its area is playing relative to the entropy of ordinary matter outside black holes. And in fact, if you consider the ordinary second law, I probably don't really have to go back to this here that I listed, and the ordinary black hole area theorem separately, you actually have serious problems with both of them. So what's the problem with the ordinary second law, that's supposed to be, one of our most stable laws in physics. Well, the problem with that law is simply that you could throw matter into a black hole. If you count only the matter outside black holes, the matter that you can observe if you stay outside black holes, then that entropy is gone, and this second law is violated. Now you could say, okay, let me keep track with my lab notebook on how much entropy went into the black hole, and then the second law should still be satisfied in this form, but that would be an awfully unsatisfactory law of physics to have, which you can't test. You can't go back in and check whether the entropy of matter is still what it was and hasn't gone down or whatever. So it would make a lot more sense to only keep track of entropy of matter outside black holes, but then it's easy to make entropy go down. On the other hand, it's obvious from the fact that I just alluded to black hole evaporation and the disappearance of a black hole, that in the quantum particle creation process, the area of a black hole can decrease. Now, I referred to area increase as the area theorem, and it is a theorem in classical general relativity, but as I mentioned, one of the hypotheses of the theorem is that locally positive energy is flowing into the black hole. In quantum field theory, though, it's easy to make states that for over limited regions of space and time have negative energy density. It turns out that the state you get in, starting with any physically reasonable state, the state that you get at late times when you've formed a black hole, will in fact have a flux of negative energy going into the black hole. In some sense, that's really obvious because energy is going to be conserved in this, well, to the extent that the black hole background is stationary, energy is going to be conserved. And I just told you there's a positive energy flux to infinity. So the only possibility is that to balance energy, is that there's got to be a negative flux into the black hole. But that decreases the area and violates this second law of black hole mechanics. So that's kind of bad for both of these as separate laws, but what you might be able to do is add the two of them and get a new law, often referred to as the generalized second law. So take the entropy of matter outside black holes and add that to black hole area, and I put back in the various fundamental constants of nature that I set equal to 1 in this, just to show you that more or less every area of physics is coming into this, and I could have put in Boltzmann constant K2 as well, but this is good enough. So what's the idea here? Well, you can decrease entropy of matter outside black holes by throwing matter into a black hole, but if you do that, you tend to increase the area of a black hole. So plausibly, this quantity doesn't increase. This is an enormous coefficient in ordinary units, so you don't have to increase the area by very much to compensate for the loss of some large amount of entropy. On the other hand, in the particle creation process, you do decrease the area, but you do that at the expense of spewing out a thermal distribution of matter outside black holes, so you increase this S. So there's at least a good chance that this quantity, in fact, never decreases, and the ordinary second law, together with the area theorem, should be, well, those two should be discarded and be replaced by this generalized second law. So does this generalized second law hold? Well, I mean, does the ordinary second law hold? There's no sort of proof of that. There are arguments for it and so on. But one of the most powerful things you could do is sort of try to test it, in this case with Gedanken experiments rather than real experiments. And if we look at, here I'm about to describe a very plausible way that we might very well, and I would claim at the classical level, can violate the generalized second law. So I'm going to start with, far away from the black hole, with a box of ordinary matter, maybe the box of gas that I started this talk with. That has some energy E and it has some entropy S. And now I'm going to very slowly lower the box so that it'll be an adiabatic process. I don't want to create radiation. I don't want to make the gas turbulent and convert energy of my lab to thermal energy in the box, etc. So I'm going to very slowly lower this toward the black hole. And then at some point when I'm decided I'm close enough to the black hole, I'll drop the box in. So that's the Gedanken experiment. So how do we do on the generalized second law? Well, we clearly lose entropy S of matter outside black holes. That's easy. How much do we increase the area of the black hole? Well, we increase the area of the black hole by the first law of black hole mechanics as the energy that goes into the black hole divided by its temperature, which is, of course, surface gravity over 2 pi. But the point is, classically, the energy that goes into the black hole is the redshifted version of the energy I originally put in the box, and that I can make, in principle, at least classically, as close to 0 as I want. That is, the chi as close to 0 as I want before I drop it in. So I can make the area increase as small as I want. And it would appear that we can violate this generalized second law, thereby, if that were the case, that would certainly jeopardize this being interpreted as entropy. So what's interesting about this process, as Bill and I showed quite some time ago, is that it doesn't work, and it doesn't work because of quantum reasons. This slowly lowered box that's nearly stationary, well, will be accelerating quite a bit, and it will feel itself to be in a thermal bath of radiation that, well, corresponds far from the black hole to the Hawking effect that I've already been talking to you about, but close to the black hole, where the acceleration is getting very large, curvatures and everything else are not getting large, it corresponds to the Unruh effect, the radiation seen by an accelerating observer. But what's relevant about that, primarily relevant about that radiation here in this case, is that the front part of the box is closer to the black hole than the back part, so it's going to be accelerating more, and it's going to see a higher temperature here than the back part of the box. So you're going to have this local temperature, but because of this redshift factor appearing in the local temperature, there's going to be a local temperature gradient. And that, if there is entropy density in the in the radiation seen by this box, as there better be, because this radiation is thermal, it's got to have at least as much entropy density at a given energy as what you put in the box, because you can't do better than thermal. That's going to give rise to a buoyancy force, which is, what good does the buoyancy force do? Well, you're recovering the energy that goes into the black hole is the original energy minus what you recover at infinity doing work. But if there's a buoyancy force, you recover less at infinity doing work, so some energy goes into the black hole, some irreducible amount of energy that goes in, and one can then show that that's just enough to keep the generalized second law valid. So going back to this table, I would say that the apparent validity of the generalized second law very strongly suggests that a quarter area really is the physical entropy of the black hole. So I don't think we need a lot more evidence that black holes and thermodynamics are very closely related, but I do want to mention some recent work of a couple of years ago that makes that connection even stronger. I'll just briefly mention this, and then I'll get into the issues of how do we understand the origin of, or how should we try to understand the origin of black hole thermodynamics. So if we have some dynamical system, we have a notion of dynamic instability of that system. If that system has a thermodynamic description, we have a notion of thermodynamic stability of that system, namely it's thermodynamically unstable if a small perturbation can increase the entropy at fixed values of the state parameters. Now, if you have a system that's dynamically unstable and thus is going to evolve away from the equilibrium state that you've put it in initially, that should certainly imply thermodynamic instability, because this dynamic instability, if it were thermodynamically stable, would require the entropy to increase as it runs away dynamically. So you'd get a violation. I forgot if I said decrease or increase, but anyway, the entropy would necessarily decrease as this in this dynamical evolution. But there's no real reason why, or there's no reason why, if you have something that's thermodynamically unstable, it need be dynamically unstable, because the perturbations that increase entropy might not be dynamically accessible. So presumably, if the underlying system is really basically ergodic, everything would be accessible, but the macroscopic dynamical equations that are being used may not incorporate what one might call the dissipative processes that you need for entropy increase. So, for example, it's not hard to get examples of perfect fluid stars that are dynamically stable but are thermodynamically unstable. On the other hand, for classical black holes, I can't imagine what sort of dissipative process, whatever that means, might occur that wouldn't be described by Einstein's equation. Again, classically, not quantum mechanically, but in classical general relativity, Einstein's equation should really be giving everything, not just some crude macroscopic description. And that, well, in some sense has been borne out by recent work that I've done with Stefan Hollins, which proves that for classical black holes, in fact, dynamic and thermodynamic stability are completely equivalent. So I think this enhances this relationship that I think didn't need a lot of further enhancing between laws of black hole physics and laws of thermodynamics. Okay, so what is the interpretation one should give to the laws of black hole thermodynamics? Well, I have absolutely no doubt that the laws of black hole thermodynamics are the ordinary laws of thermodynamics applied to black holes. And in particular, that this generalized second law that I spoke of as a generalization of, second law of thermodynamics is just the ordinary second law applied to a system that contains a black hole. Now, the thing I want to spend the remaining minutes of the talk on, though, is now how do we understand the origin, let's say, of the entropy of the black hole and the origin of its thermodynamic laws? Well, I think it is normally taken for granted that we should apply the usual concepts of statistical physics of ordinary systems to do that, and that if we could just count the number of internal states of a black hole and get that to add up to give us the quarter area as the entropy, that would be the end of the story, and we would now understand black hole thermodynamics. I don't think that's the case. I think that a new conceptual understanding of the origin of thermodynamic laws in the framework of general relativity is really going to have to come into play before we understand a little better how thermodynamics arises for black holes. In other words, I don't think that the reasons that one would give for thermodynamic behavior of a lump of coal are going to work to explain the thermodynamic behavior of black holes. So I have various reasons for believing that about how much, oh wow, okay, that's too much time. You'll see the flaws in this. I was hoping I'd only have 1 minute so that I'd have to rush through this. Okay, so these are not, truly coherent arguments of, and so on. These are to some extent vague thoughts. The first one I think is really quite weak, so wouldn't necessarily expect to convince anyone or even necessarily myself about this, but it's worth mentioning. So these are places where I think thermodynamics, in the case of black holes or more generally gravity, things are different in terms of getting some explanation of the origin than they are in usual non-gravitational physics, where one has a fixed phase space, a time translation invariant Hamiltonian, and sufficiently ergodic-like dynamics. So going back to the very first thing I said with comparing the box of gas to a stationary black hole, I mean, they both equilibrate, but it seems to me the way the black hole equilibrates doesn't really seem that analogous to the way the gas equilibrates, despite my implicit suggestion to the contrary at the very beginning of the talk. I mean, the equilibration for an ordinary thermodynamic system really involves having enough time for the dynamical system, more or less wherever you started it, to explore enough of its phase space to reach this high entropy region, which of course occupies most of the phase space. And you get an arrow of time. I mean, of course, the second law has an arrow of time built into it. That arrow of time has to do with choosing special initial conditions. On the other hand, equilibration for a black hole is, well, clearly within classical general relativity, a completely dynamically deterministic process that really seems to have nothing to do with kind of exploring enough of its phase space to figure out that it would rather be a black hole. I mean, in fact, the collapse and the settling down to a stationary black hole state occurs on, dynamical kinds of timescales, not what would normally be much longer timescales you'd need for thermal equilibration. And maybe more striking, I mean, there is an arrow of time, obviously, in the case of black holes, but that has to do with the fact that you're talking about a future horizon rather than a past horizon. Now, this I consider to be a fairly weak argument that there's a difference, because maybe when we really understand the microscopic dynamics of quantum gravity and so on, and how it gives rise to this effective notion of a black hole, we'll really see that these are more analogous than I'm making it out to be. But it does seem to be really, I mean, especially the future rather than past horizon versus special initial conditions in phase space does seem not that analogous. Okay, a second thing that I want to point out, and it's the third one that's what's really makes me convinced that one has to get a deeper understanding of the statistical physics of what's going on. But the second one is very relevant, and it's tied into the third one, which is, again, in ordinary statistical physics, we will fix a dynamical system. It'll have a fixed number of degrees of freedom, and we consider its evolution at a fixed energy, and so on. But in general relativity, in quantum field theory, in the context of general relativity in particular, I mean, one always has in quantum field theory these sort of extreme ultraviolet modes that are dynamically undergoing vacuum fluctuations and so on, but they're ignored in any calculation of entropy and so on, even though in the vacuum state, if I look at a local region, I'll have a very mixed state in that local region associated with it. And even though the sort of dynamics of the fields in the vacuum fluctuations is certainly highly non-trivial. But in general relativity, these extreme ultraviolet modes that one throws away or ignores in the usual statistical mechanics calculations can get converted to physically relevant degrees of freedom as time evolves. The most straightforward case of that is the expanding universe. There are modes in the very early universe that had wavelength much smaller than the Planck scale. I mean, of course, we don't expect our current theories and quantum field theory or anything to properly describe them, so they're in some unknown sea of something or other, and what they are and whether they have degrees of freedom, we don't have any idea. But as the universe expands, those modes, including ones that would correspond to ones much smaller than the Planck length in the early universe, are now the ones of physical interest to us. I mean, so we're not in a situation where we really have a fixed number of degrees of freedom. Things that were highly ultraviolet and kind of just, not describable in our current effective theories, let's say, now come into the phase space we're interested in, and so on. Now, this is not at all irrelevant to the Hawking process because, in some sense, the Hawking particles originated as these same sort of ultra-high frequency vacuum fluctuations near the horizon. At least in the semi-classical description, these particles that you would see coming out of the black hole, that's 3 minutes, you're also losing degrees of freedom with things falling into a black hole if you say that the matter doesn't count anymore towards the entropy, it's the black hole itself, and maybe its horizon or whatever. So there's a confusing situation with degrees of freedom not really being fixed, I would claim. Okay, but now the final thing that I have the 3 minutes for is we could ask the question, where does the entropy reside in this sort of situation? Well, the actual situation I really would like to consider is exactly this sort of situation I was describing before, where we lower a box containing ordinary matter with entropy in toward a black hole. Maybe in this case we don't drop it in. And I don't know whether, okay, this is not, I made a mistake possibly going back. This is not, there we go. Okay, so let's consider that box. I won't have to go back to the picture of it, so we can just go forward. So it's pretty clear that we've got a black hole of area A, and we've got a box with matter of entropy S that's far from the black hole. The total is this, and this entropy resides in the box, and this A over 4 resides in some sense in the black hole, although one might argue whether that this, maybe this it should be attributed to degrees of freedom inside the black hole, or maybe these are horizon degrees of freedom, or maybe one could argue that this thermal atmosphere that I referred to is really where the entropy is. I mean, I think all of these concepts have difficulties, but let me ignore that for now because I want to get to the point related to this. Okay, so now let's lower this box toward the black hole, and the optimal place to drop it in is at this so-called floating point where it's balanced by the thermal atmosphere. Well, the point is that where it's balanced at this stage, I'm not going to go back in case I can't go forward again, but at this stage where it's balanced, it's indistinguishable from the thermal atmosphere. And in fact, if you look at what has happened in this process from an inertial point of view, what's actually gone on is that the energy that was in this box has been radiated by the moving mirrors effect, even though you've moved it really slowly. And the energy that, or some energy that was in this box has gone into the black hole. So when you've lowered the box down to its floating point, I claim you must necessarily attribute the entire entropy to the black hole if you just use the A/4 relationship. And in fact, if you let the walls of the box disintegrate, absolutely nothing happens because the contents of this box, if it was perfect thermal radiation in the first place, is going to be identical to the atmosphere. What happened, now my fundamental question is, what happened to the entropy that I associated with the degrees of freedom in this box? If you were an observer in this box, you notice no change particularly, other than there's now a strong, quote, gravitational field. There's a lot of acceleration, but if you count up states within this box and so on, you're going to get the same entropy you started with. Nevertheless, I think that entropy has to be attributed to the black hole, or it must be, because that would be given by the area formula. So what started at infinity as real thermal radiation with real entropy has now become indistinguishable from vacuum fluctuations, which you would not normally associate an entropy to. So exactly what states are you really supposed to count to get the total entropy of the system? That's my main point. And before Bill stands up, which he's about to, I can give my conclusion slide, which is that I don't think there's any doubt, and I doubt if people in this room are going to argue with me, that laws of black hole thermodynamics are ordinary laws of thermodynamics applied to a system that contains a black hole. A/4, in general relativity at least, represents the entropy of the black hole. And I think everyone would agree also that we're going to have to understand gravitation and quantum theory more deeply to really understand the origin of this. The only point I'm adding to that in the last few comments is that I think we're also going to have a deeper understanding of statistical physics to account for this as well. Okay, thank you.
I have no idea how this microphone works. Do you control it back there? Anyway, we have a few questions, time for questions. Carlo?
The microphone only works if you give it to him.
Carlo. It's very interesting what the conclusion you were sort of hinting at. You didn't really give a strong conclusion, but in your penultimate slide,
I don't have a stronger conclusion.
Right, but in the slide just before this one, you were connecting the vacuum fluctuations. Now, there is a lot of work in the last several years, maybe 5, 10 years, on the fact that most of these works come from different branches of physics, condensed matter and so on, that because of quantum mechanics, even if you have a pure state, of course, you can break the system in two and you have a von Neumann entropy. And this von Neumann entropy, to start with, has nothing to do with state counting. It's just the state is just one. You just so a priori, it doesn't seem to be related to statistical physics, to thermodynamics. However, people have realized that von Neumann entropy, due to correlations between different parts of the system, does reproduce a lot of standard thermodynamics. I'm not going into that. And there's a lot of work since back in many years ago that try to relate the black hole entropy just to the vacuum correlations, either across the horizon or something like that. You haven't said anything about that.
Well, I think that would correspond to attributing the black hole entropy, to the thermal atmosphere. That would correspond, thermal atmosphere, you could say, has its entropy, or associated with its correlations with inside the black hole or whatever.
John Barrow, you showed very elegantly how black holes obey the laws of equilibrium thermodynamics, but do perturbed black holes obey the laws of close to equilibrium mechanics Onsager relations, fluctuation, dissipation theorems, things like that?
That's not something I've particularly looked at. I wouldn't be surprised that if in some approximations they would.
I think Sharma and Candelas had a go at doing this in 1975, but I don't know what happened since, what became of it.
Okay, yeah, and unfortunately I don't know either.
Tom, your question would come out of your time. Okay, well, let's thank Bob again.